Hi friends, let us see today what do you mean by a linear phase FIR filter design. To start with, let us take a problem. The problem says design a linear phase FIR filter of length 7 with a cutoff frequency of 1 radians using rectangular window. So in the problem, there are 3-4 things which have been mentioned. First, they have mentioned that we have to design an FIR filter, but they are emphasizing that the FIR filter must be a linear phase. Second thing, they are telling us that the length of the filter, that the order of the filter should be 7. And lastly, the cutoff frequency is 1 radian per second. They are also specifying you which type of window should be used for this purpose. So the window specified is a rectangular window. So we have this 5 things given to us. The linear phase, FIR filter, 7 is the order, cutoff frequency is 1 radians, and they have asked to use a rectangular window. Let us start our solution. The solution of this problem need to be proceeded in a very peculiar form. Now we need to understand what do you mean by a linear phase filter. A linear phase filter is the one in which the delay functions like tau p, that is the phase delay, and the group delay are constant. The phase delay and the group delays are constant. For an FIR filter to be linear phase, there are 2 conditions which a filter need to satisfy. Okay, so for FIR filter to be linear phase, okay, we need to satisfy the following condition. Following conditions must be satisfied. Okay, now what are those conditions? First condition is specified as alpha must be equal to m minus 1 by 2. Okay, where m is odd. Okay, where m is odd. Okay, so alpha is the phase of the filter, where alpha is the phase of the filter, or we can also say that it is a phase response of a system. Okay, so that is what alpha stands for. Second condition is h of n must be equal to h of m minus 1 minus n. Okay, so h of n is equal to h of m minus 1 minus n. This condition also must be satisfied. Now how these 2 conditions really need to be implemented in a problem, that we need to check. Okay, so you need to clearly follow these 2 conditions in this designing problem. So whenever we are designing an FIR filter, we take care that the FIR filter is always a linear phase filter, because the most advantage of an FIR filter over IIR filter is its linear phase response. So if I am designing a linear phase filter, then I will take care that the FIR filters to be designed is always a linear phase. If you want a non-linear phase filter, then instead of going with FIR, we can also design an IIR filter. So in general, whenever a design problem is asked, we always design an FIR filter with a linear phase response. So in all the filter design, we need to take care that these 2 conditions are satisfied. Now let us go back to our problem and see how to solve this problem. Now for the solution, I will first write the given. Given data is, I have the length, which is the m, is 7. Then the cutoff frequency, which is omega c, which is given as 1 radians. Okay. Then they have asked me to use the window function, that is WR. This is not omega, but let me write it as W. This is WR. R stands for rectangular window, which is equal to 1 for n to be less than equal to 7 and starts from 0 onwards. Not 7. Okay, if I consider n to be less than equal to 7, to be precise, n should lie between 0 to 6, because here I have m minus 1 by 2. Okay, so not 2, because if I go with 2, then it will be an anti-causal window. So I will go from 0 to 6 for m minus 1, not 2, because if we put 2 divided by, then it will be an anti-causal window. I am designing for a causal window. So these are the 3 datas that been given to us. Now let us go with step 1. In step 1, we need to build our transfer function. Okay, that is to obtain hd of e raised to j omega. We need to obtain hd of e raised to j omega. We need to obtain this because it's not specified in the problem. Now it has not been specified whether the filter is a high pass filter or a low pass filter. So let us consider, so let us assume the filter is a low pass filter. So the filter is a low pass filter is our assumption, because in the design, in the question itself, it is not mentioned anywhere that which type of filter they want us to design. Now let us draw the characteristics of a low pass filter. So this is my omega, which is going from minus omega to plus omega. This is my mod of hd of e raised to j omega. This is my 0. The cutoff frequencies is given as minus 1 and plus 1 radians. So I will have to pass all the frequencies till this cutoff, and I need to reject the rest of the frequency. So let us normalize the maxima to 1. So I need to pass this much of frequencies which are from minus 1 to 1, and above that till minus pi, and here till pi we need to reject the frequencies. Okay, so what will be my hd of e raised to j omega from this? The hd of e raised to j omega will be, it will be 1. Okay, and I don't write anything right now here. I don't write anything right now, but it's not complete. From minus 1 less than equal to omega less than equal to plus 1. Okay, and it's 0 otherwise. That is understood that it will be till minus pi to plus pi. Okay, where omega 1 is my omega c, that is a cutoff frequency. Okay, now what is that in bracket term? So I've just wrote something bracket, but I have made it blank. Let us understand what that bracket term stands for. Would be given as, I'll write it again. We had hd of e raised to j omega with, I have written 1 over here, and then I wanted to write something in this bracket, and then I'm going from minus 1 omega to 1, and there is something 0 otherwise, right? So I need to understand what is this bracket term means for. So let us make this bracket term. The bracket term is given as e raised to minus j alpha omega. Okay, the bracket term is given as e raised to minus j alpha omega, and here the alpha is given as m minus 1 by 2. Okay, so m is in our case is 7 minus 1 by 2, which will give me 3. Okay, now if I substituted, my hd of e raised to j omega will be 1 e raised to minus j 3 omega, that is a bracket term, minus 1 less than equal to omega less than equal to 1, and 0 otherwise. Right, so this is the hd of e raised to j omega that we have obtained from the step 1. Now let us go to step 2. In step 2, we have to apply inverse DTFT. Okay, so I will apply inverse DTFT and I will get h of n as 1 upon 2 pi integral from minus pi to pi, okay, h of e raised to j omega e raised to j omega n d omega. Okay, so let us solve that. We will have h of n, okay, 1 upon 2 pi. Now for the integral, we need to go back to our regions. So for the region, we have region number 1, we have region number 2, and we have region number 3. Region number 1 from minus pi to minus 1 is 0. Region number 2, that is minus 1 to 1, it is 1 e raised to j omega alpha omega, and from 1 to pi again it is 0. So my integral will be from minus 1 to 1. Okay, here the integral will be 1 e raised to minus j 3 omega into e raised to j omega n d omega. Correct? Now we will adjust the terms and we'll get e raised to j, I can pull common out, n minus 3 I will write together, and then omega also I can pull it common out, d omega. So that will give me value as 1 upon 2 pi, okay, integration will be e raised to j n minus 3 omega divided by n minus 3 with a j from minus 1 to 1. Then when I substitute the value, I will get 1 upon 2 pi, okay, e raised to j n minus 3 when I put the upper limit, minus e raised to minus j n minus 3 when I put the lower limit, divided by n minus 3 into j. Okay, so let us take 2 inside with j, pull n minus 3 common out and make it a sine term. So next term will be 1 upon pi n minus 3 into sine, okay, n minus 3. Okay, this is my h d of n, which is the output of a second step, and this will be infinite sequence. So now I have to go for a finite sequence. So let us go for step 3. In step 3, I will get h dash of n, which will be equal to h dash hd of n into w of n. Okay, and w of n is our w of r, which is equal to 1 for 0 to 6 and is equal to 0 otherwise. Right, so what we will do, and make a chart, write the value of n, then we will write the value of h d of n, then we will write w of n, and then we will write h dash of n, which is nothing but hd of n into w of n. Now w of n will be 1, 1, 1, 1, 1. How many times? It will be total 7 times. So 1, 2, 3, 4, 5, 6, 7. Because n will go from 0, 1, 2, 3, 4, 5 and 6. Okay. Now, as we have found this, then let us find values of hd of n till 3. Okay, let us find it till 3. For if you put n is equal to 0, in this case you will get 1 upon pi 0 minus 3 into sine 0 minus 3. Okay, minus sine minus theta will be minus sine theta. So this minus will come out and this minus from here will get cancelled over here. You will get 1 upon 3 pi into sine 3. Once you will solve that, you are going to get the answer as 0.015. Okay. Next answer is 0.145. After that it is 0.268 and n is equal to 3 is 0.318. Okay. That is what we got. Now 4, 5, 6, we don't need to actually solve this for 4, 5, 6. We will get the answers directly. How should we get that, or how will we get that answers directly? Now, as I told you that we had two conditions for a linear phase filter to be designed. First condition, that is alpha is equal to m minus 1 by 2, is utilized in step 1 itself, where I have used alpha to find the phase response of the system. So the first condition is satisfied in the given equation or given problem. Now the turn is that the second equation need to be satisfied. Second equation states that h of n is equal to h of m minus 1 minus n. Right. So what does it says? If I put n is equal to 0, then I will put h of 7 minus 1 minus 0, which is equal to h of 6. So I will state that h of 0 is equal to h of 6. So what is h of 0 that I have found? 0.015. So I will put h of 6 as 0.015. Then the next condition will be h of 1. If I put n is equal to 1, it will be h of 7 minus 1 minus 1, which will be equal to h of 7 minus 2, which is equal to h of 5. That means h of 1 will be equal to h of 5. So if I put h of 1 is equal to h of 5, then h of 1 is 0.145. So I should write h of 5 also 0.145. Lastly, h of 2 will be equal to h of 7 minus 1 minus 2, which is h of 7 minus 3, which is h of 4. So h of 2 is equal to h of 4, which is 0.268. Agreed? And h of 3 will be a special case, because here the transfer function or hd of n will reach to infinity, because I put 3 minus 3, it goes to 0. Okay, so let us not treat it right away. Let us see how we got a finite number then. Now let us multiply by the window function, which is 1 everywhere till 0 to 6. So it will give me the answer as it is 0.015, then 0.145, then 0.268, then 0.318, then 0.268, then 0.4145, and lastly 0.015. Agreed? So whenever you will get a linear phase filter, you need to actually find only half the coefficient, because half the coefficients are going to repeat itself. Okay, so this is how it works in all. So this will get replicated over here, this will replicate over here, and this will replicate the farther. So more far you travel from the center, the more farther samples value you know. Okay, so this is how a linear phase design is. Now let us see how to design this, how to find a value at n is equal to 3. Now at n is equal to 3, my hd of 3 will be equal to 1 upon 2 pi integral going from -1 to 1 e raised to minus j 3 omega e raised to I have 3, so j 3 omega or j omega 3 because n is equal to 3, and then d omega. So that will give me 1 upon 2 pi integral from -1 to 1 e raised to 0, because here when you add them they are going to get cancelled. E raised to 0 d omega. E raised to 0 is 1, so I will write 1 upon 2 pi into 1 minus of minus plus 1, so I'll get 1 upon 2 pi into 2, so 2 will get cancelled and I'll get 1 upon pi, that is hd of 3. So this is how we normally find for undefined condition. We take that value of sample at n, integrate again and get the solution. That is what the problem solution is. But we should not stop here. Finally, you should give them h of n, or we say h dash of n, which is nothing but 0.015, then 0.145, then 0.268, then 0.318, then 0.268, 0.145, and lastly 0.015. This is the 7 sample design of a linear phase FIR filter. Thank you.